Okay, maximum likelihood from incomplete data via the EM algorithm. Expectation maximization. December 8th, 1976. The paper by Dempster, Laird, and Rubin. That's a great paper that we can't miss because it's just too important. It was presented in the Royal uh, Scientific Society. Right, oops. Yeah, Royal Statistical Society, and discussed by many people, and most of them are top people in the world that are famous and have made a substantial contribution to the science of statistics. Of course, the exposition here will be slightly, if not completely different from the paper, and then later this whole notion of expectation maximization as presented back then has been reconsidered and cast as a basically a variational inference problem, but we'll go the following way. We'll need a few definitions or a few concepts. So first of all, it's the convexity, and a function is convex if uh, we have for any of the two values of x1 and x2, um, the value of the function in between them and on the line, like this is a linear interpolation between x1 and x2, and of course in one dimension it's just here. Well, that's a linear interpolation point, but in one dimension it's anywhere here in this interval. That's again convex combination. Lambda belongs to 0 and 1, and so lambda plus 1 minus lambda sum to 1. By shifting this point, we're computing linear interpolation. Well, it would have been easier to just say any point between x and x1 and x2, but what we mean is any multidimensional space as well. And in multidimensional space, x1 and x2, we have a line or vector connecting x1 and x2, and what this means is any point on that vector. So a function defined at any point on the between x1 and x2 is less than or equal um, than a linear function, a line that connects the point of at f of x1 and f of x2. So this is your f of x1 and this is one f of x2. So if we evaluate at any of the points in this interval, we evaluate the function at this point and then find corresponding value of linear function that connects the f1 f of x1 with f of x2. It works in any dimensions. Then it is less than or equal to. So basically, you can see it here. If we pick two random points on this function and connect them by a line, the function is either at or under this line. Similarly, you can define a convex set as well, that of a convex set, any line between 2 points, connecting 2 points on the curve, is inside of that set. Okay, that's convexity, simple enough, familiar enough, but give me a second. Oh, okay. There are flavors or shades of convexity. So the function on the left is convex, right? It does obey the definition, connect anything with anything, and the value of the line connecting the 2 points will be higher or equal to the function. So equal to, if we put 2 points, say if we choose those 2 points right here, they're equal. The equality is strict. F lambda x1 plus 1 minus lambda x2, which is just on this line, is strictly equals to our new function. And strictly convex is then when there is no equal possible at all. Exponential function, logarithmic function are strictly convex. For the same equation, I won't repeat it here, maybe only partially. Oh, okay, just for you. For the same equation, the value of the function is strictly lower. And technically, in this graph that I'm showing, only this function is strictly convex, but they're all both convex because change the sign, and okay, you can call it concave, but that's the same notion as in here. So this is convex, and this is also convex. So what is the difference? This can have equality, this function. This function cannot have equality, but it's strictly convex. And even stronger notion, or a different, more interesting notion for us, is strongly convex. It's when there is a single optimum. This function has an infinite number of minimum values. It is convex, but there are many solutions. Similarly, or unlike the parabola, strongly convex. It is convex. Both of them are. All of them are. And there is only one solution. Okay, moving on. So convexity, a theorem for convexity. If f of x is twice differentiable on an interval a and b, and second derivative is greater than or equal to 0 on the same interval, then the function is convex on that interval. Okay, so the thing to note is non-negativity of the second derivative, or Hessian in the general case, is important. If Hessian is non-negative, non-negative definite, then, or positive semi-definite, then we're fine. The function is convex. But in this simple one-dimensional case, it's just non-negativity. Well, logarithm minus log of x is strictly convex on 0 to infinity. Now you know what we mean by that, right? It's strictly convex. And then we introduce JENSEN'S inequality. And JENSEN'S inequality says, okay, let f be a convex function on an interval I. If points x1 through xn belong to that interval with convex coefficients, actually, lambda 1 through lambda n, non-negative, and such that they sum up to 1, then this convex function of a sum of weighted combination, of a convex weighted combination of those x's, is less than or equal to the sum of the weighted combination of the function of those x's. See, we were able to put f inside of the sum if those conditions hold. then we can do that, but only it's not an equality anymore, it's inequality. We'll get a larger guarantee to get at least as large function as before. Now, logarithm is convex function, strictly convex, if you talk about minus log. But in this case, log of a sum of a convex combination of some data on the interval where this function is convex. And that interval is 0 to infinity. So for positive or non-negative values of x, we can use Jensen's inequality and pull the logarithm inside of the sum by changing the inequality sum. So now we're ready. Now we're ready to talk about expectation maximization. We have most of the bits and pieces that we need. Let's derive the EM algorithm. So our goal is to maximize the likelihood function. L is the likelihood function function of the parameters, as you remember. Well, actually, it's the log likelihood, right? As I write it there. Equivalently, if at step n we have some set of parameters, some set to some values, theta n, we want to pick such theta that the likelihood at that theta is greater than the likelihood that we have at the current value. We don't want greater or equal to, because then we're not maximizing anything, we're staying put. And definitely we don't want less, we don't want to minimize, but we want to maximize the likelihood. That is, we want to obtain a value that is greater than what we have right now. And yet, equivalently, we want to maximize the difference of what we will have minus what we have right now in terms of the log likelihood. And just by definition, this difference equals to the log likelihood minus the log likelihood at a specific point, right? And we want to maximize that difference. I'll overload this term later in the slides, but just for you, so we want this delta to be maximum. Right, but how do we do it? This looks difficult. Well, just by looking at all of those three conditions, it's unclear how can we do it. But let's introduce random variable C. Let's introduce latent variables that are not there yet. So then our likelihood becomes marginalization over marginalization of the joint distribution P of X V. So X is our data. We are observing it. Z is our latent variable. Expectation maximization algorithm applies to the cases when we sort of fudge those latent variables. We add them to the model to simplify the process of maximum likelihood estimation. Or there are actual latent models when latent variables, when we know they're there, we just fail to observe them for some reason. So this is the joint. Our true set includes both of them. This union of those two sets, X and Z. And then we want to integrate out those random variables. And that's what we do. This is nothing but chain rule of probabilities, factoring our joint into the product of conditionals, or conditional and prior. And we're integrating out the Z. But back to our definition. We want to maximize this expression. the difference of log likelihood at the new parameter values minus the log likelihood at some old parameter values. Let's plug this in. After we do that, here's what we got. Okay, we'll see. So let's do some manipulation. Let's see. We started with our okay. So we started with our difference that we want to maximize. Log likelihood at the new value or the final solution log likelihood must be larger than much larger, as much as we can than the log likelihood as a current guess or an estimate, because we're maximizing this difference. And we just rewrote this is what we're trying to achieve, and this is the log likelihood at a given value that of parameters that presumably we can just compute, as we did with well, as you will do in the homework with the two Gaussian cases. So because when you compute that log likelihood at given parameters, you basically can compute the posterior as well. Okay, now without introducing any changes to the equation, let's multiply our joint log likelihood marginalized over z, the latent variables, by 1, namely by posterior of z at theta n divided by posterior of z at theta n. Then, after we do that, we can rearrange the equation. This goes into there. So, and well, both of them basically become, okay, I found an easier way to explain that. Basically, I take this, place it under here, while leaving this posterior here. That's what we get. Now, so we have log likelihood of this expression, and now this is, we just introduced this ratio, which is legal. Then we use Jensen's inequality, and according to Jensen's inequality, this expression is larger than or equal to that expression, log of the sum of convex combinations. Of course, this is a posterior distribution over z. When we integrate probability over z, it's 1, so everything is obeys to the conditions or assumptions of Jensen's inequality. And we have now convex combination of the log of those values. And if we pull in this minus log side, yes. And define this quantity as some delta. Then we have log likelihood of theta minus log likelihood of theta at the point n greater than or equal to this quantity that we just derived. Or equivalently, our new value is lower bounded by our old value plus um, this quantity. Okay, so this is exactly the lower bound because our new value cannot be less than the lower bound that we just defined. So when it equals to the lower bound, that means the both like it when this is the lower bound, basically again, and the values equal. Let's plug in what we get. So let's, instead of theta here in this expression, everywhere where we have theta, let's plug in theta n. And once we do, I'll get the following expression, but this is the joint of x and z, as well as this is the joint of x and z. But then we get log of 1, but log of 1 is 0, and our lower bound equals to theta n, equals to log likelihood at theta sub n. Graphically, it looks like that. So this is our log likelihood that we want to maximize as a function of theta. This is our lower bound, and when they're equal, so lower bound is lower than the likelihood, and when they're equal, they touch. So if we pick the value that maximizes the lower bound, then that is higher than where they touch, then we get to the new value of the likelihood, where we can continue the process and maximize the lower bound again, pick the new value, compute the new lower bound, and maximize it again and represent it again. So how do we do that? How do we maximize when well, we maximize the lower bound with respect to theta, and again this lower L is the calligraphic L. So we expand the expression as we've derived it and drop the terms which are constant with respect to theta. So we did, because this will be minus log of this value times that value, so this will disappear. Note that note that this log is just the top minus the bottom, and basically denominator goes into minus log, but it doesn't affect the optimization, doesn't affect maximization, we end up with this expression, and now we need to maximize this expression um, and pick a theta that maximizes the expression. Again, we okay, so what we do is, again, we do a fudge factor. This is the joint distribution right here. Okay, probably I need to write this. So probability of x, z, theta. Probability of z, theta. So probability of z given theta is the joint probability of z and theta things relevant ways by the law or rule of conditional probability, and the same probability of x given z and theta is nothing but the joint of x, z, and theta. Just rewriting, I mean, I'm not even introducing any factors there. Those two are equal, and then we can cancel this out, and what we will be left with is probability of x, z, and theta, which is the joint distribution of x and z given theta. That's what we have here, but this is an expectation of the log of the joint of our latent variables and um, the data with respect to the posterior that we estimate separately. So once we know the posterior with respect to theta n, we can plug the z's here and maximize the value, because now we have the x, we have the z's, and um, we can find theta n plus 1 that maximizes the following expression. So we run by KL divergence multiple times in these derivations, and you already know how it works and what it is. And we can have another view, or an equivalent view, of maximum likelihood optimization if we basically look at what we had and consider it under the following angle. We had our log likelihood was a lower bound plus scale divergence of our posterior, let's call it Q. Yeah, our old posterior era are new posterior distributions. So if we, well, our log likelihood is defined as before. As we started, right? Integral over z probability. Well, that would be true only if it was conditioned on Z, but we're actually marginalizing the joint, right? And once we do that, we're getting back our log likelihood, and I mean log here and log here. If we define those quantities as, well, the usual, the discrete version of KL divergence of QC over QC and posterior of the hidden values of x and theta, and define our lower bound as QC log of the joint distribution of x over QC. So this now is variational inference formulation because we are using Q, we're using Q um, as our approximation, and we're adjusting Q as an approximation to the posterior distribution. So if we define Q as posterior, then the key process, what is happening is we need theta. Theta parameters are not known, and in the mixture model, as Gaussian mixture model, we first will guess the parameters, then use parameters and the data to estimate this function, the posterior probability of the class membership or responsibilities for those, well, the posterior probability of class membership or responsibilities. Once we do that and plug in the estimate here, the KL divergence will become 0 because the distributions will be the same. We'll use the value at the current value, the current estimate of theta. But then, typical picture, thanks to Bishop, if this is our log likelihood, then it consists of two components, lower bound and the KL divergence. When we estimate the posterior distribution, we set KL divergence to 0, and now our our maximum likelihood is completely defined by the lower bound. So notice Q is here as well in the lower bound. So once we change the Q and set KL divergence to 0, we also change the lower bound. Now we are at that point where lower bound is a new function now because everything changed here. It's a function of Q, of theta, sorry. Q has changed. This is a function of theta. Let's start changing the function. This is log likelihood, and this is our lower bound. So then we maximize the log likelihood and get in here. So once we maximize the log likelihood, KL divergence also changes. It also increases. It can't be less than 0, but it increases because to maximize the log likelihood, we are changing the parameters of our Q distribution. This is the unknown distribution, right? But the Q that we can manipulate with, we know it. We're changing the parameters, we're changing theta, and we maximize the lower bound. So it's also called evidence lower bound optimization, elbow process. So okay, at the step after, like the first step, estimate the posterior, zero out, scale divergence, everything now is L, the lower bound. Then we start increasing lower bound in order to increase. That's our previous value of L theta. Let me remove that. We won't need this. Need more room. So I've increased this, and as a side effect, in the maximization step, as a side effect, I've increased my likelihood, but by my log likelihood. But my log likelihood is a sum of my lower bound and KL divergence. By increasing the lower bound, I pushed my Q outside of the optimal zero value of KL divergence. So my KL divergence is now higher. That together maximizes my log likelihood even further. But then again, I set, by changing Q, re-estimating the posteriors, I set my KL to zero. That is, I pushed my lower bound higher. And the process repeats until convergence. Very powerful algorithm used in hidden Markov models, for example, in factor models and like particle filters algorithms created for that to basically do expectation maximization algorithm. It's also a very powerful proof technique because, for example, non-negative matrix factorization that we covered in the class, the original proof proceeds similarly in a similar technique as the EM algorithm convergence proof. And then in one of my papers for extension of non-negative matrix factorization, I used a similar technique, and you will see AM algorithms again, AM is not a single algorithm, it's like a meta algorithm because you have to come up with what you are maximizing and what you are, well, that's the likelihood, and what you're finding at the expectation step. An expectation step, think about it, you're finding posterior probabilities, and maximization, you're maximizing the likelihood. I think that's it for today's lecture.